when looking at and going through and doing scatter plots, there's all sorts of types of data that we can look at, and we always want to look and say, you know, what kind of association do we see? What do we see going on? What kind of interpretation can we have when looking at this data? But before we do that, we need to just really identify other key elements of what make up a scatter plot. So in this case, we have two variables. In this case, I'm talking about GPA and SAT. And people always ask, you know, like, which is a better indicator? Really, a third variable we could put on here is college success, right? So maybe if we had a third variable sticking out, make a three-dimensional graph, we could have college success on here. But people ask, you know, are GPA and SAT scores related? And generally speaking, I'm going to kind of give you a little scatter plot here of about what you would normally see. I'll make a little bit bigger dots so you can see. Something like that. And where you say, wow, look at that. And I don't know if you can even see whether or not there's an association there, but there typically is an association between GPA and SAT, and usually there is a positive association between GPA and SAT, and it's somewhat linear. So it's not always, depending on what demographic you're looking at, it's not always a real strong relationship, but there does seem to be a positive relationship or positive association. Means as GPA increases, the expected SAT also increases. We say expected because we're making a least squared regression line, and we're going to, expect. What do we expect to see happen? We have two variables here. We've got the x and the y. The x is called the explanatory, and y is called the response. Typically, a problem will have what you'd consider to be like a logical comparison. Like, which one do you think is the explanatory? Which one do you think is the response variable? Which one do you think explains what happens and what you see happening in the other one? All right. Not always, but again, generally speaking, there is. There will be times when there's an explanatory and response variable, and they tell you which one is to use for which one. Make sure that you follow the order that they tell you when doing explanatory and response. Now, we've already talked about shape, center, spread, outliers. That is, direction, form, strength, and outliers. Let me show you quick the formula for finding R. So again, like I said and typically say, you do not need to actually know the formula by hand, but if you do know it, it starts to make a little more sense about where the calculations are coming from. So what you actually do is for every data point, suppose we have data point x1, comma, y1. And then we have ... all the way up to the last x value, x sub n, comma, y sub n. So we've got all these data points that make up my data set. If I take all of the x's and average them, I'll get an x bar value. And we'll see, and we've talked about that the least squared regression line goes through the point x bar, y bar. So what I did is I took every x value, all the way up to x sub n, averaged them out to get x bar. I took every y value, y1, y2, y3, y4, all up to yn, and I average them, and I get x bar y, and I get the value y bar. So to find R, which is a strength of linear relationship, remember, R only measures strength of linear relationship. R measures only the strength of linear relationship. And I'll say it a third time because it is that important. What does R measure? It only measures the strength of linear relationship. So R is equal to 1 over n minus 1. So it's kind of like an average, like we did with the standard deviation. And then I'm going to multiply that by everything. So I'm going to take x1, subtract it from x bar, and divide it by the standard deviation of all the x's. And then I'm going to multiply that by y1 minus y bar. Oop, that's a y bar. That's a y bar. Divided by a standard deviation of all the y's. Now if you look at each, and then I'm going to go plus. If you look at this, data point minus the average divided by the standard deviation, that kind of looks like a z-score for x. Data point minus the average divided by the standard deviation. This looks like y minus its average, the y bar, divided by the standard deviation of y. That's kind of like saying I've got, oops, wrong thing there. I have a z-score for y. So it's kind of like I'm taking a z-score for x times a z-score for y, and then I go plus. What do I go plus? Well, then I do the second point. x2 minus x bar over standard deviation of x times, and I'm running out of room, y2 minus y bar divided by standard deviation of y plus all up to the last one, which will be these numbers. X sub n minus x bar over s sub x times y sub n minus y bar over s sub y. I add all those up, divide them by n minus 1, and I get r, which is Pearson's correlation coefficient. We're never going to do that by hand, but you can see that you're taking into every data point's account how far it is from the average of that data point compared to its standard deviation, so its relative score. How far is the y value from its relative score? And I multiply them. I do that and divide by n minus 1, and I will always have a number somewhere between 1 and negative 1. So r will be some number between 1 and negative 1. And that is how to find r, the Pearson's correlation coefficient. Now for some facts. We've already said that r is no more than 1 and no less than negative 1. So what happens if I have my data set and my data points, and let's say I'm comparing distances, or like Barbie, bands to distance, and we measured in metric, so centimeters, and trust me, that says distance, that says centimeters, that says bands for number of rubber bands. What if I change my units from centimeters into inches? What effect does that have on r? Well, the answer is none. R does not change when we change units of measurement for x, y, or both. So maybe I had pounds related to pounds or inches related to inches, like how is the arm span related to height, and we change both of them from centimeters to inches, or one of them from centimeters. The answer is r doesn't change. The correlation itself has no units. That's what's so great about r. So great about r is there are no units. Because remember, it was x minus x bar over s sub x. The units all cancel. So r is unitless. So just like z-scores are unitless. So that's a unique and interesting fact about r. Correlation also requires that my variables, these have to be quantitative. It kind of I think goes without saying, but you can't take x1 minus x bar over standard deviation of x of a quantitative variable. That makes no sense because there's no measurement. This blue minus green divided by standard deviation of hair color, it makes no sense. Okay? If the data shows a clearly pattern, like that, based on what I've said earlier in this video, can I use R to describe this distribution or this graph? Can I use R to describe this graph? In your reflection response, you're going to write an answer to me. Now, do not just say yes or no. Say why. So if you say yes, we can use R, tell me why. If you say no, we can't use R, tell me why. But the answer is already in this video, and you already heard me say it. And then last thing, let's say we have this, and these are all supposed to be just single points. So even though they look like scribbles, they're points. So I got those data points. What do you think happens if I add this data point right here? What effect does that have on R? And when I say what effect, does it make R closer to 1, closer to negative 1, closer to 0, no change? Does adding that point over there do anything to R? And then, let me erase that point. No, it won't let me erase. So pretend that point doesn't exist now. What if instead of that point, we added a point up here? What effect does adding that point have on R? Again, does it make R stronger, weaker, no effect? Think about that. Be ready to answer that when you get to class, and be able to. Really, you got to be able to answer that when we have tests and quizzes. There's the real answer. So if you can't figure it out and you don't know, and we for some reason don't talk about it in class, you better make sure you're asking that question about what effect this type of an outlier has versus what effect this kind of an outlier has. They actually have two different names as we go along. That's probably enough for now. Make sure that when you're filling this form out that you answer the question that I asked you to answer, and that when you're asking me questions from now on too, I want you to be, like when I say what question do you have about this lesson, I actually want it to be about this lesson. So no more questions about my favorite football team, favorite color, favorite food, most embarrassing moment, I don't know, all the other weird questions that you want to ask me, would I rather be the Tooth Fairy or the Sandman? Yeah, I don't care. Only asking me questions, please, related to the concepts of the videos. That's it. See you in class.